Hello everyone, welcome to the session. Uh, in this session, I am going to discuss about the exam version related to the X-ray diffraction technique. So in exam, examiner may ask you write the brief details about the X-ray diffraction techniques in characterizing the meteors. In that particular situation, this session will help you to write the exam without any difficulty. So first thing, the question is like XRD. The question is like XRD. Then obviously the abbreviation XRD is nothing but X-ray diffraction. So one sentence you have to write the XRD is nothing but X-ray diffraction technique. The short form is named it as XRD. Second, this is a characterization technique or the tool to characterize the materials. Characterization techniques to characterize the materials. This is the second point you should write. Then it is characterized related to the structural properties. It discuss about the structural properties. That it mean that the structure related things, whether it is cubic or hexagonal, whether it is tetragonal, so all these information can give related to the particular material. How the atoms are distributed, that part also we can discuss by using the X-ray diffraction technique. But so it is impossible to get the nature related to the material, nature related to the morphology, to morphology. So which is not possible. Structural properties we can measure, but morphology related information we can't get from the X-ray diffraction technique. Again, XRD is the full form is X-ray diffraction and the short one is XRD. It is a characterization technique to characterize the material structural properties, but it won't give information about the morphology. Then coming to the working point of view, it works based on the Bragg's law. It works breaks based on the Bragg's law. That formula is 2d sine theta equivalents to n into lambda. Here d is nothing but interplanar spacing. Here the distance between the two planes is taken as the interplanar spacing. This is taken as the d, and theta is nothing but glancing angle. Here theta is nothing but glancing angle. You may get the doubt, just we heard about the either incident angle, what is the meaning of glancing angle? So this is the plane, this is a plane, this is a normal. For example, if the ray strikes the or meet the normal at this particular location, this one is taken as the incident angle, but this one is related to the glancing angle. The ray makes angle with the plane is taken as the glancing angle, and lambda is the wavelength of the source, wavelength of X-ray. Here if the condition like 2d sine theta equivalents to n lambda is matched, then we'll get the diffraction pattern is possible. Diffraction is possible. But what happened if the Bragg's law is not matched? It is impossible to get the diffraction condition. The peak maxima is not possible. For example, in case of Bragg's law, so in case can be applicable, next one, this can be, the X-ray diffraction can be applicable for crystalline materials. That is, it can differentiate the crystalline and amorphous materials. That is, First, we should understand what is the meaning for the crystalline and what is the meaning of amorphous materials. In case of crystalline, the regular arrangement of atoms are possible. The periodic arrangement of atoms are possible, while in case of amorphous, irregular pattern. So because of the irregular pattern, it is impossible to observe the Bragg's law condition, whereas in case of crystalline materials, there is a possibility to observe the Bragg's law. So here this is take it as the interplanar spacing, and this is nothing but glancing angle. If in this particular situation, if it match the condition like 2d sin theta equivalents to m lambda for that particular theta and for the particular d value, will get the diffraction maximum, whereas this is not possible in case of amorphous. So the intensity changes is possible for crystalline materials and that is not possible for amorphous material. Based on this information, XRD diffraction pattern is possible for crystalline, but it is impossible for amorphous material. There is no sharp diffraction pattern can be possible in case of the diagrammatic representation. That means the diagrammatic difference between the crystalline and amorphous materials is like this. For example, this pattern is related to the crystalline materials, and whereas in case of amorphous, so the broad, there is no diffraction pattern can be possible. So based on this kind of spectra, we can decide one is related to the crystalline and another is related to the amorphous material. Our question is, what kind of information we can get by using this kind of pattern? By using this kind of pattern, what kind of information we can get, how we can interpret the X-ray diffraction pattern. So for this, here I'll show you one XRD pattern which is related to the one particular crystalline material. So there is the XRD pattern. Here this is the maxima intensity of this particular peak, and this is represent the full width broadness of the peak. This is represent the broadness of the peak. If the broadness is more, that is size of the crystallites is less. Size of the crystallite is less. So the broadness is inversely proportional to the size of the crystallite. And it also gives about the crystallinity. If the sharp peaks are obtained, then we can say that the crystallinity of the diffraction pattern related to the particular material is more as compared to the others. For this, I just taken the comparison between the two materials. See here, the diffraction pattern related to this material and this material. The diffraction pattern related to the above is the broad and below is the sharp. See the comparison between the diffraction pattern of the same material. One is related to the sharp and the width is less as compared to this. Here it represent the, it has the crystallite size value less or the nano, and it is related to the bulk material, that is crystallite size is more, crystallite size is less. So based on the peak width, there is a possibility to understand the size of the crystallites present in that particular material. And the positions of these peaks is decided by the condition like 2d sin theta equivalents to n into lambda. For different set of planes, we are having the different d values, and theta is related to the glancing angle, n is related to the order of diffraction, lambda is the source. And coming to the structural parameters point of view, there is a possibility to measure the crystallite size. Crystallite size can be measurable by using the Debye-Scherrer formula. d equals to 0.9 into lambda by beta cos theta. Here the beta is nothing but the full width of maximum. For example, this peak, this width is related to the for total width. Full width of maxima is taken as the beta, theta is the corresponding angle, and lambda is the source, and zero point 0.9 is the shape factor. This formula is obtained by Debye-Scherrer relation. So by using the Debye-Scherrer formula, there is a possibility to measure the crystallite size. And second one, strain, that is deformation within the material, can also be possible to measure. E equals to beta by 4 tan theta. By using the same beta value and theta value, there is a possibility to measure the strain parameter. And in addition, there is also possible to measure the interplanar spacing d value by using the condition like 2d sin theta equals to 2d sin theta equals to n into lambda. By knowing the theta and lambda and n, there is a possibility to measure the d value. By obtaining all these values, there is also possible to measure the d value is equivalent to 1 by square root of h square by a square plus k square by b square plus l square by c square. By using this relation, there is also possible to measure the lattice parameters a comma b comma c. For in case of cubic crystal, a equals to d equals to d into square root of h square plus k square plus l square, as a equals to b equals to c, which is possible in case of cubic material. That's what, in the place of a square, b square plus c square, we are using a square. Then we'll take it to the upward. Then a equals to d into square root of h square plus k square plus l square. So this is about the X-ray diffraction pattern importance in characterizing the materials. This is the short revision, especially for the exam point of view. If you want to go in deep manner, there are different structural properties can be measurable by using the X-ray diffraction technique. Thank you.